Okay, so we are about to take a look inside the mind of an AI. But here's the twist. We're not going to use code. Nope. We're going to use geometry. We're going to peel back all these layers of abstract math and, believe it or not, find something you can actually picture. Real, tangible shapes that show us exactly how an AI makes its decisions. All right, let's kick things off with a puzzle that has honestly baffled AI experts for years. You've got companies spending millions, literally millions of dollars, training these gigantic, super complex neural networks. But here's the weird part. It turns out that a much, much smaller, leaner network that's already hidden inside can often do the exact same job just as well. So how is that even possible?
Well, the answer, or at least a big part of it, lies in this really brilliant idea, and it has a fantastic name that just perfectly captures the whole concept. It's called the lottery ticket hypothesis.
So the theory goes something like this. Imagine that inside every huge, super complex AI, there's this smaller, way more efficient little network just waiting to be found. And finding that special subnetwork, it's like finding a winning lottery ticket in a giant roll of tickets. The real trick, of course, is figuring out which of those connections are the lucky ones. And for the longest time, this was a total mystery. Researchers knew these winning tickets existed, they could find them sometimes, but they just couldn't explain why. What made certain little networks so special? It kind of makes you wonder, right? What if we've been looking for the answer in completely the wrong place this whole time?
Okay, so let's try a completely new angle. We're going to set aside all the code, forget the complicated network diagrams for a minute, and instead, we're just going to start thinking about shapes.
Now, this is the core idea from a really groundbreaking paper. These researchers proposed that maybe, just maybe, the secret isn't hidden in the network's connections at all. What if it's in the actual geometry of the problems the AI is trying to solve? And this image right here gives us a perfect way to picture that. Think about it. For an AI to do its job, say, classifying data, it has to draw some kind of boundary to separate the red dots from the blue dots. And that boundary, well, it isn't just a random line. It has a distinct shape. That hidden geometry, that's the key. Okay, but to actually see these hidden shapes, we can't just use regular old algebra. We need a special kind of mathematical lens. And I gotta say, it has a very, very unexpected name. It's called tropical geometry. Yeah, I know, it sounds a little strange, right? But it is the absolute perfect tool for this job. It's basically a whole different way of doing math that totally simplifies complex functions. What it does, essentially, is it ignores all the smooth, swooping curves and instead reveals this kind of hidden skeleton of straight lines and sharp angles that's hiding underneath. Okay, so the first rule is incredibly simple. I want you to forget everything you learned about addition in school. In tropical addition, you just compare two numbers and you pick the bigger one. That's it, seriously. And the second rule? Just as straightforward. What we normally think of as multiplication, well, in this world, it just becomes regular addition. So with these two new rules, max instead of plus, and plus instead of times, we suddenly have this brand new lens to see how a network actually makes its decisions. So what happens when you apply these new rules? Well, you don't get those smooth curves anymore. You get what you're seeing right here, these distinct angular shapes called tropical hypersurfaces. See those red lines? They're all straight, and they create these sharp corners. And here's the big breakthrough. It turns out these geometric shapes are a perfect match for the decision boundaries inside an AI. All right, so we've got our lottery ticket mystery on one hand and this cool new mathematical tool on the other. Now, let's connect the dots and see the big picture. And here it is, the big reveal. Using this tropical geometry, the researchers proved that an AI's entire decision-making process can be represented by a single, tangible geometric object. It's called a polytope, which is, basically just a fancy word for a shape that exists in multiple dimensions. Suddenly, it's not just abstract code anymore. It's a real shape that we can actually look at and analyze. This really is the core breakthrough, and this quote from the paper just says it all. The really complex, hard-to-understand behavior of the AI is now directly tied to the clear, predictable geometry of this polytope. They've bridged the gap between this abstract behavior and a concrete, physical shape. And look, this isn't just some cool theory. This is the real deal.
Now that we can actually see the shape of an AI's reasoning, we can use that knowledge to solve some of the biggest puzzles in the entire field.
So let's go all the way back to our original question about those lucky little networks. What actually makes a subnetwork a winning lottery ticket? Well, the answer, as it turns out, is all about geometry. A winning ticket isn't random at all. It's the one specific subnetwork that best preserves the shape and the orientation of that original polytope. Just look at the example on the left. The smaller shape is like a perfect miniature of the big one. But on the right, you see what other methods do. They just scramble that shape, and that totally destroys the network's performance. The luck was in the geometry all along. But this whole geometric view, it doesn't just solve old mysteries. It gives us really powerful new tools for building better, more efficient AI, like right now.
Okay, take network pruning, for example. That's the whole process of making an AI smaller and faster. Before this, it was kind of a guessing game. But now, it's basically a visual problem. You can just look at the polytope and see which parts of the network are redundant. If getting rid of a neuron doesn't really change the overall shape, you know it's safe to prune it. And the data shows this really works. I mean, look at the highlighted row. When the researchers tested their tropical method against other standard techniques, it got a higher AUC score. And that's just a metric for performance. A higher score means it did a better job of keeping the AI accurate while making it way more efficient. The proof is right there in the numbers. This geometric view even helps us understand something like AI security. An adversarial attack, where a tiny, almost invisible change to an image can totally trick an AI, we can now see what that really is. It's an attack that just slightly warps the decision polytope, just enough to push a single data point over to the wrong side of that boundary. So what does this all mean in the end? Well, it means we finally have a key to that infamous black box of AI. For so long, its inner workings have been a complete mystery. But by translating its abstract logic into concrete geometry, we're finally making it understandable, predictable, and way more controllable. And this all leaves us with a really exciting question to think about. We've uncovered the hidden geometry of one type of network, but what about the massive, world-changing AIs we're building today? What other hidden, fundamental shapes are still out there just waiting for us to find them?